Have you learned how to use calibration curve in uh, studying unknowns from GenChem or from any other labs?
Yes.
Briefly.
Okay. So we know that when you do quantitative analysis, you always have to deal with unknown samples, right? Which means that you probably, when you have an instrument, you will go ahead and get a signal corresponding to the unknown sample. But how to exactly convert the signal to the concentration of the sample? For that, you have to use known samples to establish a calibration curve that can give you a reasonable correlation between the instrument signal to the sample concentration. Right? So many analytical methods generate calibration curves that are linear or linear in nature. And the idea behind it is, if you have, like, when you do the known solutions or standard, you run a series of different concentrations, right? And with each concentration, it will correspond to a certain instrument measurement. And what you want to do is you want to generate a linear line which can try to fit all the data, all the measurement of the standard solutions. But in reality, it's impossible to make sure all the merit value are on the line, right? So the idea comes from to find the best straight line. And what does it mean to be a best straight line? You have to determine the best fit to the experimental data by minimizing the square of the deviations. What is the square of the deviations? So think, assuming that this is our theoretical fitting, and this is our real measurement data. The deviation from the fitting would be the deviation in the y value, the difference between the measured value to the estimated value from the fitting line, right? And if you have to write the equation, it will be the square of the deviation, which can also be written as the yi, which is, so this is for every data, this is your yi, and this is the y from the fitting line. Okay, and for example, if you're using Excel will automatically generate the line by running an algorithm to make this value minimized. Okay, this is the definition of it. And so this shows the example, right? When you have randomly distributed data, and you can try to find a best fit, and you can see that for a best fit, some of the data are on top of the lines and some of the data are below the lines, right? So you can like cancel out the standard deviation, or not cancel out the standard deviation. You're trying to minimize the overall deviation from between the measured value and the estimated value. And if you have used Excel for generating calibration curve, you're probably familiar with a parameter which is called R square, right? That is a value for evaluating the linearity of the fitting, which is called correlation coefficient, which is R square. Okay, so R square compares the sums of the variation for the y values to the best fit 9y variation due to the variations to a horizontal line. Okay, this sounds a little bit complicated, but overall, what it means, it means that when you generate this line, okay, when you generate this fitting line, and if the x changes, if your x value changes, because x is a variable, is the independent variable. For example, concentrations, right? When your concentration changes, the y value should also change, right? And if you already fitted to a linear line, for the linear line itself, all the changes in y value is because of x change, right? Because we have a formula which is y equals to mx plus b, right? So when when we detect a difference in Y value, let's draw a line here, okay? If this is a linear fitting line, and if you compare this one A and this one B, B is larger than A, right? But why is B larger than A? It's because B is correlating with a larger concentration, right? In another word, any difference and any variance generated in B in the y-axis is because of the change in x-axis. Does that make sense? Right? So the y is linearly dependent on x. But in reality, your measured data doesn't necessarily follow that, because the measured data can include some random measurement error. So it could be slightly higher than your estimated value or lower than estimated value. The yi, okay. So yi is, for example, I have 4 concentration, 1 ppm, 2 ppm, 3 ppm, 4 ppm. And this is our instrument measurement, for example, intensity, okay? The first data is somewhere here, second data somewhere here, third data here, and fourth data here, okay? And when you do the linear fitting, it's probably something like this, okay? Well, this one is already on the line, so the deviation is 0. But if you're looking at this one, this is our y2. Okay? If this is y1, this is y3, this is y4. It's actually x4, y4, x2, x3, y3. When you do the plotting here, this is your x3 and this is your y3. Okay, right? And the y3 just means the y value of the third measurement. And the deviation we're looking at is the deviation between the y3 and the theoretical y. Does that make sense?
Yeah.
Okay. All right.
Oh, just one more quick question. So can the calibration curve also be called the trend line?
Yes.
Okay.
Yeah. Where did I stop? Anyway, so what I was trying to explain, maybe this figure will give you a better idea. So if you compare this two figures, okay, as I mentioned earlier, in the fitting line itself, the y variation is purely due to the horizontal variation, right? Does that make sense? In the fitting line itself, because it's a linear dependence. So the y change is always correlated with the x change. But in a real measurement set, for example, if you look at this one versus this one, okay, we can see that this A is much larger than B. But if you look at the concentration or the x variance, they're mostly at the same spot, okay? So the difference in A and B are not due to the variation to a horizontal difference. For example, a concentration difference, right? Or in another word, with the same concentration and you do 3 measurements, you can probably get 3 different values, okay? So what causes the change in the values? What could possibly cause A and B to be different, even though they are from the same concentration? Anybody?
Random error?
That's right, Cindy. It's random error. So random error can generate the 2 different values, even though they are from the same mean. So what R squared is measuring is actually they're trying to compare the variance for the Y values to the variance to the linear fitting Y variance. And if your R squared is 1, it means that all the variation in the Y value from the measurement, it's the same with the linear fitting, which means that all the changes in Y value is correlated with the concentration change or whatever in the x-axis. So for this one, for the first example, you can see that R squared is almost 1, and you get it means that you have a much better linear fitting, right? And for the second one, R squared is less than 1, it's 0.5. And you can see that for the first one, 99.5% of the Y variation is due to X variation. But for this one, only about half of them is due to the X variation. And the other half is caused by the random distribution, random measurement error, okay? All right, I think we are, the time is up. Again, I will stay for a few minutes for further questions. Otherwise, I will see you on Thursday. Thank you, everyone.
Professor.
Thank you.